So, hope you have tried to solve this. What does this last term means by yourself? What is the answer you will get? It will be 0, right? How? Those couldn't do it, or if you don't remember your classical mechanics classes, I can write it down as qi dot is equal to what? Dou h by dou pi, and pi dot is equal to, or rather I would write minus pi dot is equal to dou h by dou qi, right? Therefore, dou qi dot by dou qi is equal to dou squared h by dou qi dou pi, which can be written as minus dou pi dot divided by dou pi, right, based on this expression. Which means that dou qi dot by dou qi is equal to minus dou pi dot by dou pi, which means that this term will turn out to be 0. So therefore I can write dou rho by dou t plus this term, right? What is qi dot? Qi is equal to dou h by dou pi. Yeah, so therefore, based on this expression, now I can write dou rho by dou t plus rho h is equal to 7. The Poisson bracket rho h is equal to 0. What is Poisson bracket? Poisson bracket rho h is equal to summation over I equal to 1 to 3n dou rho by dou qi into dou h by dou pi minus dou rho by dou pi into dou h by dou qi. Right, this is the expression which you must have studied again in your classical mechanics class. Rho h, the Poisson bracket rho h the Poisson bracket rho h is equal to summation over I is equal to 1 to 3n dou rho by dou qi into dou h by dou pi minus dou rho by dou pi into dou h by dou qi. So therefore, from here, this expression I have reached to dou rho by dou t plus Poisson bracket rho h is equal to 0. But this term, this left hand side, dou rho by dou t plus rho h, I can write this as d rho by dou t, d rho by dt, right? So you have a local term and its variation. So therefore, this is the total differential. So d rho by dou t is equal to dou rho by dou t plus rho h, which means that d rho by dt is equal to 0. So what is the significance of it? This is our original Liouvilles theorem, which we were intending to prove. D rho by dt is 0. So the Liouvilles theorem is now being proved. So you have the total rate of change of rho in the vicinity of its selected points, which turns out to be 0. So that is what we just proved. Now Um, now let's discuss it a bit more in the detail. One of the similarities or the analogy which people talk about in the books um, is that the d rho by dt basically represent change in change in density function as seen by an observer moving along the trajectory. Let me first of all write it down. D rho by dt represent change in density function moving along the trajectory. I'll try to explain it by using a figure. This is a schematic figure. Don't extend it to various different more critical situations. This is really a figure so that I could explain you well what is the meaning of this and the observer moving along the trajectory and all that. Now, so this is my entire phase space, okay? And we have decided a random volume phi during the initial part of our derivation. Now let me put the trajectory like this. This is a trajectory. Of volume y, phi. Right? So now I have to explain this. This is just for this figure and all those things are not to be written in the exams. This is just for your understanding purpose. Now I put a viewpoint here. You know with viewpoint, right? When you go for trip and all that, you have the viewpoints. So you can stand on the viewpoint and observe the things, what all things are going around you. So that's a viewpoint. So I put a viewpoint over here, and I put another viewpoint over this. Over here, and I choose two representative points M1 and M2. Okay. So I have two viewpoints and I have two microstates M1 and M2. Imagine that at time t1 I am at the viewpoint 1. And at time t2 I am at viewpoint 2. At time t1 I am at viewpoint 1, and at time t2 I am at viewpoint 2. Which means what? I am actually moving. I am moving along this trajectory. So initially I was here. After some time I reach this second viewpoint. Right. So at time t1 I take the I try to see a very local microstate. Actually, I am not sitting on there. I am very far. I am in the viewpoint. But if I look into this viewpoint at time t1, I measure this microstate. So at time t1, I take my first measurement sitting on the viewpoint 1 on the situations around me and also a local microstate m1 and m2. And I carry out the same experiment at t2 where I sitting at the viewpoint 2, I look the situation around and also the local microstates m1 and m2. So what does this Liouvilles theorem is telling is that when I am sitting at the viewpoint 1, the distribution of microstates around me, see I am here, are same as that of the distribution of microstates around me when I am at viewpoint 2. So either I am at viewpoint 1 at time t1 and if I am at viewpoint 2 at time t2, the distribution of microstates around me is the same, right? That is what the d rho by dt is equal to 0 means. You can, if you want, you can play it once more and try to appreciate what I told you. So I am sitting at viewpoint 1, I am seeing a distribution of microstates, I noted it down. After time t2, I reached the viewpoint 2, I measured the I took stock of the microstates, distribution of microstates around me, and I found that the distributions at viewpoint 1 and the viewpoint 2 are absolutely same. That is what the d rho by dt is equal to 0 tells you. But, and also another information which I noticed was that since the system is in equilibrium, what I noticed was that when I was at viewpoint 1, I looked m1 and m2. And I noted down what is the microstate m1 and what is the microstate m2. After t2, when I reached viewpoint 2, there again I measured m1 and m2. And I found that both m1 and m2 remains same in my both measurements. That is what the dou rho by dou t is equal to 0 means. The rho does not change locally with respect to time. So that is what the d rho by dt and the dou rho by dou t is equal to 0 means by. Okay. So that is it. That is how you try to understand this expression. D rho by dt is equal to dou rho by dou t plus rho h is equal to 0. So for a system in equilibrium, my dou rho by dou t will be 0. So what does it mean by? My d rho by dt is equal to 0. And also I know that for a system in equilibrium, dou rho by dou t is also equal to 0. Which implies that my rho h should be now be equal to 0, right? D rho by dou dt is 0, Liouvilles theorem. Dou rho by dou t is equal to 0. My observation and also the condition for a system in equilibrium, which implies that based on this expression, my Poisson bracket rho h is equal to 0. Okay, so what does that mean now? Poisson bracket rho h is equal to 0 for a system in equilibrium. What does that mean? That means that So it will be possible only when my rho is independent of Q and the P. Q and the P. Or my rho of QI is equal to 0, is equal to constant. It's a constant for a system in equilibrium. So rho of QI is equal to a constant for a system in equilibrium. What does that mean by? Rho of QI is constant for a system in equilibrium, which means that my rho does not change with time. What is rho? Rho is my distribution of microstates. So as the time changes, my distribution of microstates does not change, or it's a constant for a system in equilibrium. It does not depend on Q or the P. This means that the number of microstates or the density of microstates, which means that I can now write down a strong statement that microstates are uniformly distributed in an ensemble at any point of time. Right, actually it will be more correct if I write possible microstates. So possible microstates are uniformly distributed in an ensemble at any point of time. That is what my this rho of QIPI dot is equal QIPI is equal to a constant is telling me. Now right. So this condition, if this is to be valid, where the rho is independent of Q and P, this situation will be valid only when only in a microcanonical ensemble. Why? So this situation where the rho is totally independent of the Q and the P, which means that my the elements in my ensemble should be totally immune to the changes outside or the energy inside, right? Because this Q and the P, how will it play out? It will play out through the Hamiltonian, right? H of QP. So this is how the Q and the P will play a major role in your system. Now H is a factor of the Q and the P. Which means that my rho is totally independent of the Hamiltonian this factor is not changing with Q and P, which means that my energy is constant. So energy is constant means this is a microcanonical. Ensemble, and this is really an ideal situation where but we have the uses for the microcanonical ensemble, so therefore we still use that. So in a microcanonical ensemble, I have what? Rho of QP is equal to a constant. This is just what we wrote above, right? 1 second. Rho of QP is equal to a constant. So this is what just we wrote over here. Under what condition? If my E minus delta by 2, H of QP is lying between a particular constant value E minus delta by 2 to E plus delta by 2. Actually, energy is not allowed to change, right? So rho of QP is, so this is the condition for microcanonical ensemble. Rho of QP is equal to a constant. If my system is, the Hamiltonian of my system is existing within a energy limit. Otherwise, this is equal to 0. This rho of QP will be 0. It will not be constant, but it is 0. So this is the valid condition for a microcanonical ensemble. The energy has, Hamiltonian has to exist between, we should have a constant energy. But we do allow for a delta by 2. You should remember that this delta by 2 is very small compared to the is very small compared to the energy, but we do have to allow some kind of a delta. This will basically release the microcanonical ensemble from some kind of an extreme idealization. In the real world, almost every system has to be in contact with its surroundings, however it's small baby, but that is the situation. So therefore, even though we tell that the energy has to be constant, we do allow such kind of a small delta as the delta by 2 as the limit in which the energy is allowed to change. So rho of QP is equal to a constant in that limit, or otherwise it is equal to 0. Now, so that is about the microcanonical ensemble. So if this was, if rho h is equal to 0 is possible only when it is independent of Q and P. But now if it was really dependent on Q and P, right, if the rho was really dependent on Q and P, then again it will come through something called the of a Hamiltonian, or the energy expression. So the rho of QP will come through rho of HP, and H of rho of HQP, and therefore that will suggest something like the canonical ensemble, where the energy is allowed to change for my system. That we will come across through in the next set of videos. So here in this video we dealt with the system, which is microcanonical ensemble, where you have the rho is totally independent of Q and P. Next we will deal with the situations where the rho is dependent on the Q and P. There we may introduce the terms like the partition function and all that, and we will have that we will expressly show the connection between the partition function and the way in which the partition function or the density functions, similar term, how it varies with the Hamiltonian. It is basically exponential variation, which we will see in the next classes videos. So that is it for this first one. So this Liouvilles theorem is basically applicable for the microcanonical ensemble. That's what I believe in. And okay, so we will discuss the rest of the stuffs in the class.